Hello, my name is Abdul Dakkak, and today I'd like to talk about DLSpec, a deep learning task exchange specification. This is joint work with Cheng Li, Jinjun Xiong, and Wen-mei. First, let's start with some background. Deep learning is a fledgling field, and as such, deep learning innovations are introduced at a very rapid pace. Currently, however, there is a lack of standard specification. This makes it hard for authors to share their models, users to reproduce them, and it also makes it difficult to perform a fair comparison of these DL innovations. The current practice of publishing DL artifacts makes it difficult to reproduce, try, and compare DL innovations. The current practice is comprised of publishing source code, ad-hoc scripts, and textual documentation on code-sharing repositories such as GitHub. Frameworks, for example, curate DL tasks in a model zoo to demonstrate the capabilities of their framework, thus being framework agnostic. Similarly, cloud providers have model catalogs that users can use, again to demonstrate the capabilities of the provided cloud platform. But this again is vendor agnostic. Model authors also sometimes publish their code for others to test, although it's less structured than what the framework and cloud providers have. Therefore, it's very hard and inconsistent to compare. Because of the lack of specification, it is hard for others to reproduce reported accuracy or performance results. It is also difficult to perform consistent and fair comparison across DL artifacts. A specification would be a step towards the right direction. With the motivation out of the way, let us discuss what a specification for DL tasks would need. A specification would encompass all aspects of a DL task for it to be an artifact exchange format. The four aspects of a DL task are the model, data, software, and hardware. Since those aspects are constantly changing, the specifications needs to be model, dataset, software, and hardware agnostic. Since the specification needs to be run, we need the specification to be compatible or able to leverage existing MLOps tools. In this paper, we developed DLSpec, a specification for DL tasks. We demonstrate the practicality of DLSpec by developing a runtime for it. The runtime uses DLSpec specification for DL inference tasks in the context of benchmarking. We designed DLSpec on a few basic principles. We will describe these principles in the next two slides. First, DLSpec needs to enable reproducible evaluation. This is a core requirement of the DLSpec design. DLSpec also needs to be minimal. This increases the transparency and the ease of creation of these specifications. We therefore designed DLSpec to only contain essential information for users to reproduce a task with the expected outcome. We designed DLSpec to also be program and human readable. This makes it easier for users to determine what execution entails for a DL task, and it also makes it possible to develop a runtime that executes a DL specification. DLSpec also needs to have broad expressiveness, and this makes it capable to express both DL training and inference. Because while DL training and inference tasks can share many common software and hardware setups, there are subtle differences when specifying their resources, parameters, inputs and outputs, or metrics. There are a few additional principles that DLSpec follows. DLSpec decouples DL task description. A DL task using DLSpec is described from the aspects of model, data, software, and hardware through their respective manifest files. Such decoupling increases the reuse of manifests and enables the portability of DL tasks across datasets, software, and hardware stacks. DLSpec also splits the DL task into pipeline stages. The stages of in this pipeline are the pre-processing, run, and post-processing. Using a pipeline design enables consistent comparison and simplifies accuracy and performance debugging. For example, to debug accuracy, one can modify the pre-processing or post-processing steps and observes the accuracy discrepancy. And to debug performance, one can surround the run stage with measurement code. Finally, DLSpec is designed to be efficient. It avoids the need to serialize intermediate files within the pipeline into files. Avoiding the serialization to intermediate files is needed to support DL tasks that use streaming data. The DLSpec key principles informs this design. Here we show a design overview. We will delve into each of these components in the next few slides. A DLSpec consists of 4 manifest files or specification files, along with the reference log files. All of these manifests are versions using a semantic versioning scheme and have an ID, which means they can be referenced later on. The first manifest we'll discuss is the hardware manifest. The hardware manifest defines the hardware requirements for a DL task. The parameters in the hardware manifest form a series of hardware constraints that must be satisfied to run and reproduce a DL task. The hardware manifest also allows users to specify hardware settings that they are unable to specify within the container environment. This is shown in number 2 in this example. For example, it's not possible to turn off Intel turbo boosting within a container. Thus, DLSpec allows one to specify hardware configurations in the hardware manifest that allow the runtime to set them outside of the container environment. The second manifest described is the software manifest. The software manifest defines a software environment to run the DL task. All executions here occur within the specified container. Thus, the software manifest specifies the container to use for a DL task, as well as any other configuration parameters that must be set. For example, framework environment variables. The framework or other library informations can be listed within the software manifest. These are purely for ease of inspection and management. The third manifest to describe is the Dataset Manifest. The Dataset Manifest defines the training, validation, or test dataset used for a DL task. The source location in the manifest defines a remote resource to download the dataset from. This remote resource can be hosted on an FTP, HTTP, or a file server, such as Amazon S3 or Zenodo. These remote resources have an associated checksum, which is used to verify the download. If the dataset is an archive, then it's automatically extracted. The final manifest is the model manifest. The model manifest defines the logic or code to run a DL task and the required artifact resources. The model's manifest specifies information such as the model assets, graph and weights, the pre-processing and post-processing steps, and other metadata used for the evaluation. The pre- and post-processing are run stages that are defined as Python functions and are embedded within the manifest. We do this because the DLSpec runtime can use the Python subinterpreter to execute this Python code within the current process, thus avoiding using intermediate files. Using Python function also allows for great flexibility. For example, Python functions can download and run Bash and R scripts, or download and compile some C++ code. The input and output fields within the model manifest file define the ports to use for executing the model and informs the runtime how to call the frameworks. For example, the data types of the tensors to use. Note that the flexibility of specifying the network ports and allowing arbitrary processing functions means that DLSpec works with existing pre-processing code and is capable of supporting arbitrary input and output modalities. Finally, the model network and its weights are stored as a remote resource along with their checksum. As with the Dataset Manifest, the DLSpec runtime downloads the remote resource and validates the consent checksum provided in the manifest prior to running the model. It is up to the runtime whether to cache the download or not. Finally, aside from the manifest, DLSpec describes a reference log. The reference log is provided by the specification authors for the others to refer to. The reference log contains the IDs of the manifest used to create it, achieved accuracy or performance of a DL task, expected outputs, and other author-specified information, such as the hyperparameters used for training. The reference log is an artifact of a DL task. That is, when run with any combinations of the four manifests described. Let us now look at a broader picture of how the four DLSpec manifests are used when running a model. First, the user uses the hardware manifest to run the model on. The user then runs the specified code that needs to be run outside of the container, as specified by the hardware manifest. The user launches a container specified within the software manifest and sets up the environment variables defined. The dataset manifest is then used to install the dataset within the container. This includes downloading the dataset from the remote resource as specified. The model manifest is then used, and for each item in the dataset, the pre-processing code is run. The preprocessed data is then made to match the tensor's form that's expected by the model. Once pre-processing input setup is complete, the DL task is ready to be run. First, a check is made if the task is for inference or training. If it is an inference task, then the model weights are downloaded from the remote resource, and the checksum is checked as specified. If the task is training, then it may not be necessary to download any model resource. The user code is then executed to run the model, and the model outputs are returned. Model outputs are then read from the network ports as specified, and post-processing is run as well. Since the DLSpec manifests are program readable, the above can be automated via runtime with no human intervention. We designed a runtime for DLSpec. This runtime is described in a paper called The Design and Implementations of a Scalable DL Benchmarking Platform, which is published in IEEE Cloud 20. We call this runtime MLModelScope. In brief, MLModelScope is a distributed runtime that uses DLSpec manifests to ensure a repeatable and scalable DL inference benchmarking. MLModelScope provides either a web or a command line portal to these DLSpec manifests. It uses a distributed registry, database, and tracer to ensure scalability. It is framework agnostic, supporting popular frameworks such as Caffe, Caffe2, TensorFlow, TF-Lite, CNTK, MXNet, TensorRT, and PyTorch. It is also hardware agnostic, supporting PowerPC, x86, and ARM, with GPU or FPGA as used as accelerators. It is also OS or system agnostic, supporting desktop settings, edge, or mobile. To conclude, an exchange specification such as DLSpec enables a streamlined way to share, reproduce, and compare DL tasks. DLSpec takes a first step in defining a DL task for both training and inference, and it captures the different aspects of DL model reproducibility as for specification. We are actively working on refining the specification as new DL tasks are introduced. On behalf of Abdul, Cheng, Jinjun, and Wen-mei, thank you.